student friends, I'm back again with another video on quantum mechanics. This video is in continuation of an earlier video on wave function associated in matter wave. This is part 2 of this particular videos. As in the last video we have shown how the wave function can be physically interpreted, and where we encountered this kind of conditions there. If we consider equation like this for infinite space, volume of space, or finite volume of space like V1 to V2, or in one-dimensional finite space, we always find that the right hand side is always equal to 1, because the probability of our whole space is maximum and it's equal to 1. So this condition is known as normalization conditions. And definitely this normalization condition represents the fact that the probability is a finite kind of thing. Now sometimes that this may not be equal to 1, just like this, and in that case we multiply this particular expression by a constant 1 by n moduli square, such that this constant compels these conditions to be removed, and ultimately this new wave function psi square by psi by n moduli square dv equal to 1, or representing psi by n by another wave function psi 1 square, psi 1, that is psi 1 moduli square dv is equal to 1. So we come to conclude that this is a normalization conditions. In the particular cases where this is not equal to 1, we compel to make it, and we do it by putting by multiplying with some constant, say 1 by n moduli square. And this happens like this, where this psi 1 is a wave function which is nothing but the original wave function psi divided by n. And this simply represents one thing, that to preserve the normalization conditions we always have to multiply with some constant, and that particular constant may be a real kind of thing or maybe a complex thing. But since this is multiplied with a wave function and we are taking the moduli square wave function, so ultimately we'll be having with the real value of that particular quantity, because modulus of a complex thing also become a real thing. And sometimes we we take that constant instead of 1 by n, we take that constant as either n or 1 by root square n or square root of n. So in all cases the right hand side will become 1, just like these things. And for multiplying the wave function with a constant n, and we get a new wave functions like this, or for 1 by square root we get this, or for square root of n we get this. So for every case, since these wave functions are arbitrary wave functions, so wherever we take it's 1 by n, just like here, or n into psi, or 1 by psi by square root of n, or square root of n into psi, in every case the normalization condition will be satisfied. So this normalization constant does preserve the fact that the probability is always equal to 1. This is some more concepts of normalization, and since normalization condition is always, as we said earlier, that it's because the probability is always finite and is equal to 1. This is for an infinite volume of space, this infinite quantities here. This is finite volume of space V1 and V2, and this is for one dimension which is finite. For infinite dimension it will be minus infinity to plus infinity. And we can understand now that we have to normalize the wave function to make the probability finite and to make the probability maximum equal to 1. And also in some cases did modulus square of the wave function into some volume constant and integrated over whole space, or for one dimension cases is always equal to 1. We don't need a normalization constant there. But if it is not happening there, that this is not equal to 1, just like this, we have to multiply this by some constants, either 1 by n or 1 by square root of n or square root of n, whatever well, we like to choose. This normalized wave function normalization condition is so valid for whether it is time-dependent wave function or time-independent wave function. So, with an example, we can understand this. The ground state of hydrogen atom, which will take care in later course of time, is given by this U over 1 by n e to the power minus r by n naught, and this r represents the radial distance and n naught is a constant. And if we normalize this for finite volume space, then we get a condition like, since a spherical polar coordinate system, where dv is r squared dr sine theta d theta d phi, and we have three coordinates here: r ranging from 0 to infinity, theta ranging from 0 to plus pi, and pi ranging from 0 to twice pi. So with all this, we get the right hand side is always equal to 1, and since with some standard integrals we can find that this particular integration gives us 4 pi. So this multiplying this quantity by 4 pi, and then which is the standard integration of e to the power minus twice r by n naught r squared dr, which is with the help of gamma function. We see that this integration would give us 2 factorial divided by 2 by n naught square is equal to 1, and ultimately we find that this 1 by n molar square is equal to this, 1 by n molar is this. So our normalization constant is equal to 1 by square root of pi n naught, and since 1 by n modulus is equal to this, so our normalized wave function is this. Now we may ask that why we are putting this normalization constant. If we don't put this normalization constant, we'll see that we have to integrate this expression just like in these cases, and we'll find that this particular expression will lead to a value that which is not equal to 1. So in that case, the right hand side is always equal to 1 because its maximum probability is 1, but the left hand side will not give us 1. So that's why we have to bring a constant and choose that particular value constant in such a way that the left hand side also became equal to 1. So here is our conclusion. When this quantity is unity, then the normalization constant is 1. So this is the condition that we first encountered. If this is equal to 1, this means the normalization constant is 1, and we need not to normalize the wave function. But if this is not equal to 1, that is, if the condition is like this, in that case we have to bring some normalization constant. That is what is written here, and the normalization constant is so chosen that this particular thing becomes unity because the probability is 1 for over whole space, and also that wave function is normalization because that this quantity is finite, that is, the probability is finite over whole space, and its maximum value is 1. So lastly, we are left with an assessment. What is meant by a wave function? It's a mathematical entity, and moduli square of it gives us probability density. Then interpret the wave function physically, what we have already done. What is normalization? Just discussed here, that the wave function, moduli square of the wave function integrated over whole space, whether it is in finite space or finite space, giving us 1, and this is equal to normalization. And its need is that it keeps probability finite. And what is to be done with a wave function if it is originally not normalized to unity? So we have been asked about the condition that if it is not equal to 1, the right hand side is not equal to 1, just in the last example. So we have to use the normalization, we have to bring some normalization constant and choose its value in such a way that the right hand side is always equal to 1, as well as the left hand side. And the different conditions for well-behaved wave functions, which we have discussed in the last video, and also the justification for them, just starting from the finite value of probability, then probability current density, and the finiteness of potential energy. With all this, I'm ending up this video. Hope that this video is useful for you. Keep watching our videos. Never forget to comment on our videos. Thanks once more for watching our videos.